Now, you probably don't want to touch something that's so hot that it's literally glowing, right? You don't want to touch hot things in general, but if you see like an object that's like literally glowing by how hot it is, you're gonna know, yeah, I don't want to touch that. And that's pretty crazy, right? Like objects with high temperature, or really any temperature in general, can emit electromagnetic radiation. And why is this, right? Like, why do hot things glow a certain color, or in general just emit infrared radiation? Well, if you think about an object, right? Let's say I have a box or something, and I'll draw this a bit bigger. But if I have an object, this thing is made up of molecules, and if it's at a, I don't know why I'm making this so, whatever, we have an object, right? If, it's at a certain temperature, its molecules are going to be moving. And because, if you think about a molecule, maybe this is made up of salt, why not? It's made up of salt. And if you think about the NaCl molecules within here, they have charges, right? Each molecule is made up of two, or in this case, with salt, each molecule has two atoms. Electrons and protons are going to be a part of those atoms, and they're going to be moving around and vibrating. And because they're kind of moving around and I don't know how to show that they're moving around and vibrating, but because they are moving around and accelerating a bunch, you get electromagnetic waves, because the electric field is changing. That will induce like a changing magnetic field. That's electromagnetic radiation. Now, that in and of itself is interesting. But why is it that when hot things get really, really, really warm, why is it that they emit light? Why don't all things emit light? Well, most things are really what we call black bodies. Now, black bodies, in a simple way, it's really anything that emits all kinds of wavelengths in terms of electromagnetic radiation, right? A box or a star or, the earth or most objects, they're not just emitting only like red light, right? Like at one specific wavelength. No, the movement of molecules is random. It's going to be electromagnetic waves with all sorts of wavelengths, right? So you're going to get all sorts of wavelengths coming from a black body. That's, I guess, kind of what a black body is. And because of this, there's going to be visible light, but there's also going to be kind of infrared light and UV light. And the whole consensus is that my feet were about to die there. But the whole consensus is that, well, although a black body will emit kind of, these markers are so bad. I need new markers so bad. This is a graph. I don't know if you can tell because it's pretty dark in here, but let me turn on the lights. You know what? Let's do that. There's going to be certain wavelengths, right? If you were to graph like the waves emitted from a black body, there are going to be all sorts of wavelengths. And let's say I want to map kind of the distribution of wavelengths. So, I'm pretty, you can do this by looking at intensity, right? Like what wavelengths have the most intensity. And what you find is that there will be kind of like a max amount. So if you had a black body, right? Let's say this is the sun. There's going to be a certain lambda max where even though it's producing, waves with all sorts of wavelengths, there's like the most intense, I guess most frequent you can think about, wavelength, right? Like most of the intensity of the wave comes at this wavelength. That's what the lambda maximum is. So, what we found is that, I'm looking at the labs, making sure I'm covering everything. What we found is that lambda max ends up being inversely proportional to, so lambda max is going to be inversely proportional to temperature. The actual equation would be like lambda max equals b over t, where b is a constant called Wien's constant. He's a scientist who kind of thought of this stuff. So it's inversely proportional to temperature. So what that means is, as your temperature increases, your lambda max actually goes down. And if your lambda goes down, right, the frequency goes up, because that's it's a constant speed, right? The speed of light. Now, does the speed of light change with different temperatures? I don't know, but at that specific temperature, whatever the speed of light is, right, it's going to be kind of constant. So if lambda goes down, frequency goes up. And obviously, there's like a visible light spectrum, right? So not all EM waves fall into that. So the reality of it is that most black bodies, right? If you think about people, if you think about I guess your car, if like your car engine, if you maybe not your car engine, but if you think about most things that emit electromagnetic radiation, right? They're gonna be emitting EM waves that actually have a lambda max outside, and I didn't draw this perfectly, but there's gonna have a lambda max outside this visible inside this visible light spectrum. So hey, that's why we feel hot. We still are a black body, right? Like humans are still black bodies, but because we are not super hot, this T is generally pretty low. That's a pretty high lambda. This is going to be infrared waves, and in infrared waves we can sense as heat. Like we process infrared waves as like heat. So that's kind of the why we don't glow. We just don't have a high enough temperature. As your temperature gets bigger and bigger and bigger, this graph will have a maximum that actually falls within the visible light spectrum. And this will be, and you can calculate the range of temperature in Kelvin if you know the constant, if you know, you can plug in like the boundaries, I guess, right? Like the minimum wavelength, max wavelength, and then find that range. You can do that. It's going to be a pretty high temperature, right? And because it's just a pretty high temperature, that not everything's going to be glowing. So when you see something that does glow by heat, it's very hot. That's kind of what I'm getting at here. And if you want, let's say you want to make a light bulb that can be like super efficient and super like it can just maximize brightness, right? Like you want to get a bright, efficient light bulb. Well, you'd think that, hey, according to just general wave theory, hey, I want to make a light wave. Well, if I want it to be bright and efficient and like just a great light bulb, I would want a really big amplitude, right? I would want, a really big kind of amplitude. Well, that would be brightness for light. That's kind of what I'm getting at, to get a really big amplitude. And that an amplitude is related to energy. So just from our old classical wave theory, you would think that, hey, I need a high temperature to get high brightness, right? I need a high temperature, wait, that's not what I mean. Well, I guess that would. Now I'm contradicting. I'm going off a question here in the packet. The question, you want like a, you make like a light bulb, right? And you would think that, well, hey, high temps. You would think that high temps should lead to more brightness, while low temps should lead to not a lot of brightness, right? Because of that connection between temperature and energy, right? They're one of the same thing. Or I guess temperature is like the average kinetic energy, and your light bulb is like sorry, what am I saying? Wait, what am I? Okay, wait. Let me think my thoughts before I say them. Maybe that's a good thing I should do. But what I'm trying to get at is, you would think that, like, well, high temperatures would lead to high energy, and high energy leads to high brightness because that's how it is. So you would think of, hey, instead of making a 500 Kelvin light bulb, let me make a 3000 Kelvin light bulb. Surely it'll be brighter because it's hotter. Well, if you plug in like 3000 into this equation, you get your lambda max is actually going to be outside the visible light spectrum. It's going to be infrared. So that thinking of, well, let me, get a high temp, and, I'll probably need more voltage to supply that light bulb because it's at a hotter temperature and it's going to be more resistive. Well, hey, that's fine because, I'm going to get so much brightness, but it's not really efficient because most of your wavelengths being produced by that light bulb end up being like outside the visible range. It's mostly infrared. You see light, right? I'm not saying there's no light because there's still waves. Like if you have a max here, there's still waves that exist in the invisible, but you're not getting the maximum amount. So if you're debating about whether, well, should I get a 100 Kelvin light bulb or 1,000? No, you want 1,000, right? Like LEDs, they don't produce a lot of heat. And you would think that maybe, and I'm not an engineer, so maybe this stuff is kind of wrong, but the whole idea is that temperature is related to the max wavelength, and that's really the intro to blackbody radiation. Sorry for the little like yapping at the end, but hopefully this kind of made sense. I hope. If it didn't, then maybe you could watch another video. All right, or maybe I'll just make another one. I don't know. Thank you for watching. Bye.